So now we should come back to this.
Yeah. So we'll pick some problem.
We'll pick some problem, right?
Yeah.
So maybe before we pick the problem, no, maybe what we'll do is we'll draw a simple network. Maybe we'll choose one of these sources, show an example of how it might be used. Then we can take an example.
Yeah.
So what we'll do, so suppose which one of these shall we use? Shall it say VCCS?
Yeah.
Or why not? You pick.
Or the first one.
First one itself, no? CCCS.
Current control current.
Current source, right? So what we'll do, we'll show an example of where it might come like in a network. So suppose I'll take something like this. So this was one of the simplest problems we took last time. So we have V1, R1, V2, R2 and R, something like this. Now we could also add, let us say, a current control current source, no?
Yeah.
So what I could do, I could add, let us say the network, I could have a current control current source like this, and I could say that this current is Ix, and I could say K times Ix, and this is my network now. Now what happens, the current through this current source is some gain scaled version of this. So now solving it, we need to take into account this K times Ix also. It becomes a little bit hard. So we need to set up the equations carefully.
Now the dependence is more clear.
Yes.
Okay.
And you can have many, no? So you could, I can imagine, so for example, so suppose I added a voltage controlled voltage source here, right? So suppose I said that minus plus
KVS.
Instead of K, shall I use something else? We already use K.
Yeah.
So maybe P times let's say Vx, and that Vx could be, let us say, like this.
Oh, drop across that resistor.
Drop across this resistor, something like this. So that current or voltage, the controlled variable, can depend on any other voltage or any other current inside the network. So it can get very complicated very quickly. It is not obvious on seeing the network what the values of the currents and voltages are. So you, in these cases, you really have to sit down and solve the equations very carefully.
So this analysis that we learned before, Nodal,
Yes.
etc., I can use those in this also?
You can use those because we only used, we used three things, no? Three sets of equations to solve. So, so
those are
from very
KCL
basic physics, around KCL, KVL. So we use KCL, and that we said in steady state there is no accumulation of charge at any node, and we said KVL because potential difference between 2 points is the same irrespective of which path you go to. And then we used device characteristics. So Ohm's law, right, for a resistance, or we used phasor domain, Ohm's law for inductances and capacitances, something like that. So we wrote down the voltage and current equations using these three, right?
That means then it should be
exactly. KCL, yes.
We just have to take care of these K, Ix, etc.
That's all. So what we need to do is KCL, KVL we still have to write. This device, no. We now have more devices, they have their own equations, we have to incorporate those, that's all. Our solution will not change drastically.
Yeah, got it.
Yeah. Now we should do some examples?
Yeah,
Okay.
Shall I pick?
Yeah, please, please.
I have one. Let's say there is a 15 ampere current source.
Current
DC,
source.
DC.
DC and independent, no?
Yeah, going up.
15 amperes.
So then from there, 1 ohm resistor is coming down.
1 ohm resistor.
Then an dependent current source.
Dependent current source, okay.
So that is 3I1.
3I1.
The current source is upward direction
Oh, upward direction, okay.
in this problem.
In this problem. Okay, we'll do it exactly as the textbook says.
Yeah. And then the top resistor is 1 ohm.
1 ohm.
From the top, a 2 ohm is coming down. Then this 2 ohm and the 1 ohm is connected through a 3 ohm.
Oh, okay.
And then the 2 ohm at that junction is connected back to.
Oh, I see. Okay, this is connected.
Yeah,
Okay.
So I1 is the current through the 2 ohm.
Through the 2 ohm. In which direction?
Downwards.
Downwards. Okay. And I can see clearly the direction of the controlling current matters. Right?
If this flips.
If this flips, this current direction will also flip, no? So I can see that the direction matters. So I am saying if I1 were, let us say, minus 2 amperes, then the current going upwards would be 3 times minus 2 minus 6, which means the current is actually flowing downwards. Okay.
So the question is the power supplied by the dependent source.
Oh,
Yeah.
nice question, right?
Yeah.
So the power supplied by the dependent source will be its current time voltage.
Correct.
Correct?
Correct.
So maybe we should just start there. So what they are saying is find out this Vx, let us say.
Yeah.
So Vx times 3I1 is the power
Correct.
supplied, right? P is Vx times 3I1.
Yeah.
Okay. We need to find out both I1 and Vx.
Yeah.
Okay.
We can do
One thing, go ahead.
basic nodal analysis.
Nodal analysis we can do. But one thing I realized, if you did not have this, first instinct would be to try to, simplify the network by combining resistors in series or parallel.
Correct.
But now you have to be careful.
Yeah.
Because you need to keep track this I1, you cannot lose it by simplifying.
So, superposition then will it be complicated?
It will get a little bit complicated. That's right. Because dependent sources, just like independent sources, are not linear. And they are active.
Yeah.
They are not linear. So we cannot use it directly. We have to, there are some situations where it can be used. In most situations, it cannot be used directly the way we have been doing it.
Because as long as current I1 is there, this 3I1 will be there.
Will be there, exactly. So,
Okay.
so we just have to write KVL, KCL and solve it.
Yeah. Nodal we will try.
Nodal we will try. Okay. So, actually nodal often is very easy and useful, right, compared to mesh.
Correct.
Because you can go wrong and subtracting the currents and so on. So, we will use nodal. So, 1, 2, 3 nodes.
Yeah. So, yeah.
I see 3 nodes.
And the reference.
Reference. So, shall we just use this as a reference?
Yes.
We'll just use this as a reference. Okay.
So, if we get node 2 voltage, that is enough.
We get node 2 voltage, that is enough.
I1 also.
Correct. In fact, now that we are given as a reference, 3 is the same as the reference because this thing is closed.
That's true.
Right? So, we don't need a third node.
Yeah.
I think we are easy.
Correct.
Only 2 nodes. In fact, that itself tells you for this network, your instinct to use nodal was very good. Because if you had to do mesh analysis, you will have to solve 3 meshes, set of 3 equations. Nodal analysis is much better for this.
So,
okay.
Shall we write for node 1?
Yes.
Node 1 voltage is V1. Huh?
V1.
Okay.
So, we will call this V1, we will call this V2 which is Vx.
Yeah.
Right?
Yeah.
So, this is V2.
Yeah.
Okay. So,
V1 minus V2 by 1 ohm.
Correct. So, that is this current flowing downwards.
Yeah.
So, V1 minus V2 by 1 ohm.
Then V1 by 2.
Plus V1 by 2, correct?
Equal to
15 amperes, which is coming in. 15. So, I'll just remove the units. I think we understand that it's in amperes.
Correct.
So, I'll just keep it like this. So, we are basically adding this current and saying that that is equal to this current.
Yes.
Right? That's very straightforward.
Yeah.
Okay. And now we can also write the equation at node 2. This is 1.
Yeah.
At 2, sum of these 3 currents, no?
Yeah.
So, what we will say, current going up is V2 minus V1 by 1.
Correct.
V1 by 1 plus V2 minus 0, so V2 by 3
by 3
is equal to the current coming in,
3
which is 3 I1. Okay, we already have a problem. We have 3 variables, only 2 equations.
So, but 3 I1 we can represent, or I1 we know from node 1 equation.
From node 1 equation. So, we already know that I1 is V1 by 2.
Yes.
Right?
Yeah.
So, maybe we will just write it like that.
Yeah.
So,
We can say equal to.
3 V1 by 2.
Yeah.
Okay. Okay. So, we will just rewrite it on the next page.
Yeah.
Okay. Okay. So, first what we will do,
We'll copy.
we will copy over and write. Better to do that. Correct. Always better to do that. We will copy over both of these. We will keep this as a reference.
Yeah.
Okay. So, 3 V1 by 2
Yeah.
and minus V2, no? So, let me do one thing. We will just multiply across by 2. I don't like fractions.
Yeah. Yeah.
Right? So 3 V1 minus 2 V2. Right? So, we will multiply across by 2.
Yeah.
So, we will get 2 V1 plus V1. So, 3 V1 minus 2 V2
Yeah.
is 30.
30.
So, that is the first equation.
Yeah.
Here what we will do, we will multiply across by 6, just because I have 3 here and 2 here. So, I will get 6 V2. So, let us do minus V1 alone. Oh,
So this V1 goes there, no?
goes there. No, in fact, you can get a direct relationship between V1 and V2.
Okay.
You don't even need to eliminate. So, this one is saying, so V2 plus V2 by 3, no? So, that is this, no? This equation has become this. Because I1 is V1 by 2.
Yeah.
So, V2 plus V2 by 3 is 4 V2 by 3 will be 3 V1 by 2 plus V1, right, which is 5 V1 by 2. Is this correct? I am taking minus V1 to this side, it will become plus V1. So, 3 by 2 V1 plus V1, so 5 by 2 V1. This is V2 plus V2 by 3, which is 4 V2 by 3.
Oh, so you are saying this can be substituted in.
This can just be substituted there, I think. That may be easy, no? So, it will be 15 by 8. Huh?
Yeah, I think both ways it.
Both ways works,
Yeah,
no?
yeah.
I don't think it is that.
Yeah.
So, this is a fairly simple problem. 15 by 8 V1. We can put it here, right? So, 3 V1 minus 15 V1 by 4 is 30, because we had 2 times V2,
Yes. Yes.
right? 12 minus 15 is minus 3, 4 3s are 12, 12 minus 15 is minus 3 by 4,
Yeah.
V1 is 30.
One,
So,
two, yeah.
120 by 3, which is 40, minus 40 volts.
Okay. That is V1.
That is V1.
Oh, we actually want V2.
We want V2. We should have solved for V2, I think. That's okay. So, V2 is 15 by 8 times V1, no?
Yeah.
So, 8 5s are 40, 75, no? Is this correct? 15 by 8 times 40. 8 times 5 is 40, 15 times 5 would be 75.
Yeah.
So, minus 75 volts. Okay. And now I1 also we need to find.
That is V1 by 2 or something.
3 V1 by 2. Oh, no, sorry. I1 was just V1 by 2.
2.
Correct. So, was just V1 by 2. So, which is minus 20 amperes.
Okay.
Okay. Oh, now it is easy, no? Vx is just V2. 3 I1 is 60 amperes.
Both are negative.
Both are negative. So, this power becomes positive still. So, let us see. How did we choose this? Both are negative because of this current source, I think. Because this current source is pulling out 20 amperes.
Okay.
It's trying to pull out 20 amperes. This is only able to supply 15 amperes, the independent source. I think most likely that is why it's becoming negative. I1, its current is flowing like that because of this dependent source. Okay. So, that is why. So, both V1 and I1 are becoming negative.
So did we calculate the power?
No, we have not calculated it yet. So Vx is V2 minus 75.
Oh, so it's a 75 into
Minus 75 into minus 60. So this is
minus 60 because it's 3I1.
it's 3I1, correct. So this is positive power. So this is actually delivering power, correct. And so 75 into 6 is let me see, 375 plus 450. Sorry, 4500.
Or 75 into 2 is 150.
150, 450.
Yeah.
So 4500. Okay. But solving this question now, one of the questions you asked me triggered a thought. Is this 15 ampere delivering power or absorbing power now? Because this seems to be delivering a lot of power, positive power, no? I am curious about whether 15 amperes is delivering power or not.
How we will know? If V1 plus V2 is negative.
Correct. No, one side is reference and V1 is negative, no?
Yeah.
So it looks like
So
15.
V1 is anyway
V1 is anyway with respect to ground only.
Correct.
Right. So I think now we already know that this was minus 40.
Oh.
This is an interesting problem. It looks like the dependent source is delivering so much power. Some of it is going into the current source. Current source is actually getting charged. Some of it is getting dissipated in the resistor.
Anyway,
So
I think it's a problem.
It's a problem.
It may not be.
It may or may not be practical.
Yeah.
Right. It is very rare that you see a situation like this, right?
Yeah.
Where the dependent source is producing.
Because the voltage source receiving current, I can understand.
Exactly.
Current source receiving current.
Receiving current. No, current source is receiving voltage in the opposite. It's receiving power. Right. What is this? 15 fours are 60, no? 600 watts, no? Is this correct? 15 fours are 60.
Yeah.
So the power it is getting is 600 watts. So it is actually, you are right. It is a little bit kind of this thing, no?
Yeah.
So 600 watts. And I1 was 20 amperes.
Yes.
So this is 20 squared, 400 times to 800 watts. We'll just write that down. And now this one V1 minus V2. V1 minus V2 is 35.
Yeah.
Plus 35.
Correct.
And doesn't matter. 35 squared times 1.
Yeah.
Right? It should add up. To
That it will add.
That it will add up, of course. Right? So, very interesting. Because you also need to calculate the current through the 3 ohm and then add I square R for that as well. But yeah, so.
So there was some funny question somebody asked me. So there are some 2 boxes, black boxes.
Okay, okay,
You have one is with voltage source, one is with current source.
okay.
Practical voltage source and current.
Practical voltage source
No
and current
load
source.
is connected.
Okay.
So he asked me, can you find out which one is voltage source?
Okay, okay. That's interesting. That's interesting. So actually, you said practical voltage source, practical current source, and we have said that source transformation means that they are equivalent, no?
Yeah.
So maybe it has a series resistance.
Correct.
The current source has a shunt resistance.
Correct,
It doesn't
correct,
matter.
Yeah, so current source has a shunt resistance.
Has a shunt resistance. Oh, I understand. We are talking about power.
Yeah.
So it must be related to power.
Correct.
Right? I think the current source will be warm.
Yeah, exactly.
Is that right? It will be warm because there is always current flowing through the
so
Norton
touch
resistor.
one will be little bit warm.
Little bit warmer. Correct.
Anyway, that's just a funny question.
That's funny. That's a very funny question. Correct. Okay. So good. So this thing is now we know, right? Now the students realize how relatively straightforward it is to solve these problems. You just need to add this extra equation that represent this 3I1 in terms of the other voltage variables.
I would like to see whether we can use superposition also.
Sure.
If it is if we have dependent sources.
Absolutely. Let's try it out.
Let's try. So I have a 10 volt DC source.
10 volt DC source. Okay. Polarity is which way?
Plus minus, top plus.
Top plus minus. Okay.
10 volt.
10 volt.
Then from the top I have a 2 ohm resistor.
2 ohm resistor.
Now current source,
Normal
normal current
current source, no?
or independent
Current source, correct.
Sorry, upwards.
Oh, upwards, okay.
They are connected.
They are connected, okay.
Then from the top a 1 ohm resistor.
Okay.
Then it's going to a dependent voltage source
In series, no?
towards downward.
Or downwards?
Yeah. Plus on the top side, it is 2 Ix.
2 Ix. And what is the current source value? I forgot to ask.
I did not mention. 3 ampere.
3 amperes. Okay.
Then it is connected.
Then it is connected. Okay.
Ix is the current going through the 2 ohm.
From left to right?
From left to right.
Is this correct?
Yeah.
Ix is this current?
Yeah.
Okay, great.
Actually, the question is to find out Ix.
So
Using
question
superposition.
using superposition. Okay, let's do it. So I can clearly see that the voltage of the controlled source, no, dependent source, depends on the current through Ix. And the current through Ix anyways is a linear combination of the voltage source and the current source. So I suspect that superposition must be valid here.
Okay.
Right?
Okay.
That the two voltages will just add up, but let's try it out.
So in general, what is it? If we have dependent source
Yes,
and independent sources,
correct.
when you apply superposition, you will apply dependent source or independent source or
Okay. So what we should do is, so what we do, like if we did not have any control sources,
then it was easy.
it was easy. What we would do is we would apply each one,
And take the response.
take the response, and what we would say is all other voltage sources are shorted, all other current sources are open. Right? Those are for independent.
Correct.
But for the dependent one, we can't do that. We would just use it like any other resistance or inductance or capacitance in the network.
Okay.
We will just continue to have that dependent voltage source or dependent current source there in the network and solve it in each case.
So it's the same.
It's the same.
Means response corresponding to each independent source we will find out.
That's correct.
That's it.
That's it.
The dependent voltage or current source, I don't have to worry.
You don't have to worry too much. You don't have to specifically worry. It will be very straightforward.
Okay. Then it's I have some clarity.
Yes. So let's solve it.
Yes.
Let's solve this using superposition.
We will try for the 10 volt source.
For the 10 volt source first. So one network would be like this, 10 volts, then the 2 ohms, the 3 ampere is open circuited, so 1 ohm, and this is the other voltage source, which is 2 times Ix, and now this is Ix.
Yeah.
And this is 2 ohms and 1 ohm. Okay. Well,
So Ix is 10 minus 2 Ix.
10 minus 2 Ix. So Ix is basically difference between the voltages. So 10 minus 2 Ix
by 3.
by 3. This is straightforward.
Okay.
So 5 by 3 Ix is 10 by 3.
Okay.
Right? So this is correct. So 10 by 3 is on the right side.
Yeah.
This 2 by 3 Ix I took it to the
Goes
left.
other side.
So 1 plus 2 by 3 is 5 by 3.
Yeah.
So that's what I did. So Ix is 2 amperes.
So this is maybe Ix1.
1. Maybe we'll call it Ix1. Ix1, Ix1. Right? Just call this Ix1.
Okay.
So now we have the second case where you only have the 3 ampere source. So and this is only 3 amperes. So the network becomes, we'll short the 10 volts. So we have 2 ohms. We have the 3 amperes, 1 ohm, and the dependent source. 2 times Ix2. Now
Ix we have to mark. No?
Ix we have to mark. Now we have to be careful.
Hmm.
We can't do source transformation here,
Uh-huh. Hmm.
right? We'll lose Ix2.
Yeah.
Ix2 will go internal.
Correct.
So that may be, you won't be able to keep track of what Ix2 is. So
But we can do source transformation here.
we can do source transformation here if you want. Correct? That we could do. So that is one way of doing it, right? The other way of doing it is, I think, nodal analysis at the top will really give us the answer,
Yes.
right? That is probably the easiest.
Easiest.
So we'll just keep
V1.
V1, we'll call this V1. So at this V1 node, we will apply KCL.
Yeah.
So the current going into the node are Ix2 plus 3 amperes. So, and the current leaving the node is V1 minus Ix2 by 1 ohm. Sorry, V1 minus 2 Ix2.
Yeah.
Right? So this is one equation. Well, we need another equation, no?
Yeah.
So that comes from here. So we should have, well,
Or Ix2 times 2
yes,
is minus V1.
is minus V1. That is the other equation,
Will that
right?
work?
We should just directly put that in here,
Okay.
right? So that will give you this Ohm's law for this 2 ohm resistor. So V1 is, we'll put that together with minus 2 times Ix2. We'll put these two equations together and solve the question. So let us do it now. V1 is minus 2 Ix2, right?
Yeah.
And
That will become 4 Ix.
minus 4 Ix2. We have Ix2 here. So 5 Ix2 is minus 3 amperes. So you can solve these two. So maybe I'll just copy these two to the next page.
Yeah. Yeah.
So minus 3 by 5 amperes. So like minus 0.6 amperes. And well,
Here we had 2.
2 amperes.
So
So
2
2 minus 0.6, 1.4 amperes.
Yeah.
Okay. Okay, great. So that seems very straightforward. We didn't have to do anything special, no?
Yeah.
So we have resistors, we have capacitors, we have inductors. We also have a dependent source. We just continue to use it like anything else.
Okay. Nice. Oh. Now I am curious. I mean, what will happen if I use Thevenin and etc. Thevenin, Norton.
Thevenin, Norton. Ah, okay. So two things we have to keep in mind. I think we have seen you can't remove the controlling variable, change it completely.
Yeah.
Like you can't do source transformation for this.
Yeah.
Things like that.
Because of course VTH will be okay to
Correct.
find out.
Correct.
But RTH may be tricky.
RTH may be tricky.
We'll take one simple example.
We'll take one simple example. Correct.
I've seen some. Let me. Yeah, just to find out RTH alone.
Sure. Sure.
So I have a current controlled voltage source.
Current control voltage source.
It's a voltage source.
Okay. So
Plus minus.
this is okay.
Yeah.
Okay.
It's 1.5 I.
1.5 I. Okay.
Then top side a 3 ohm resistor.
Oh, okay.
Then a 2 ohm resistor downwards.
Okay.
So that is closed. Then yeah, a little bit more. Actually, that's the AB. It's,
Oh, this is AB.
yeah.
Okay.
And this current I
Mhm.
is the current here from 3 ohm to A.
Like this.
Not there.
Ah.
Sorry.
Oh, here.
Yes.
Okay.
Yes.
I. This is I.
Yes.
Oh, this is an interesting problem. Okay. and we need to find out the equivalent resistance RTH across AB.
Yeah.
Right? Okay. Okay. This is going to be hard, right? We are used to problems where you just use series parallel and find out RTH.
Correct. Now what will I do?
So one way, we have actually seen this in the previous course.
In fact, we discussed
also there, where what you can do is, if you have an equivalent resistance RTH across AB,
or
right?
if I had to measure,
if you had to measure
what I would have done,
what you would have done, correct? And what we said is you can do many different ways. One of them is to maybe put a unknown voltage source.
Yeah.
So you have some V that you know, you apply, the current has to be V by RTH.
Yeah.
This was one. And you can also say, you could do
inject 1 ampere.
Inject 1 ampere. So that is a very good way, right?
So whatever voltage you get will be the
perfect. That's right. So you inject 1 ampere. This voltage has to be 1 times RTH.
Yeah.
This voltage will also be RTH.
Correct.
That's right. That's a very classic way of doing it. We can do either. Actually, we should try 1 ampere. It looks nice because you actually have here, it's a problem meant for that.
Correct.
Right?
So it's like we are measuring.
It's like you're
You are
measuring.
injecting 1 ampere, seeing what's the voltage.
Correct.
V by I.
V by I. Correct. Shall we try this for this
nice.
problem? It's a nice problem. Let's try it out. So what I'm going to do, I'm going to inject 1 ampere like this.
Yeah.
Okay.
Like this or
Why not? This is I.
then
So that I will be 1 ampere like this. So
I can
then
do the other way also.
you can do the other way also. Then the voltage developed will
For
be
the
like
comfort
this.
you have taken this.
For comfort I have taken this way.
Okay.
Right? This voltage should be RTH. Correct? This resistance should be RTH. Or this voltage will be RTH if the Thevenin resistance was RTH. That's what we are trying to say. Okay. Well, actually this makes it a lot easier. If it's 1 ampere, this is just 1.5 amperes.
Correct.
Right? Sorry, 1.5 volts. It's a voltage source, no? Current controlled voltage source. This is 1.5 volts. Now we can do source transformation for this. Right? Or do we really need to do source transformation? It's too simple, no? Nodal is also fine. So what we'll do is, let us say B is the reference. No, A is the reference now, no? How do we want to do it? B can also be reference. Why not? This is your reference. And so
V1 minus 1.5.
So we'll say, let's say this is V1. So V1 minus 1.5 by 3 plus V1 by 2 is equal to minus 1 in this case. Minus 1. So this already tells us V1 is 5 by 6 V1 actually. Let's is minus 0.5, no, this is. So plus 0.5 minus 0.5. Right? Minus with a minus sign. Right? 6 5s are 6 into 0.5 is minus 3 by 5. Okay. So V1 is minus 3 by 5 volts.
So that is minus, and so it's
so VBA is 3 by 5 plus 3 by 5. So we are interested in VBA, no? This is basically minus VAB. Sorry, this is basically VAB.
Correct.
V1 is VAB.
Correct.
So R Thevenin is minus VAB because it's VBA. So it is plus 3 by 5 ohms. So correct, no?
Correct.
Okay.
If I had applied the current in this direction also,
you would have got the same answer. Actually, we can try it out. Well, let's quickly do it. Let's apply the current in the other way. We'll see what happens. So I'll take the same circuit. We'll just show it. Sometimes it's useful for students to see that you will get the exact same answer. So we'll do like this.
correct.
So This is R Thevenin, the voltage. So now this current I is minus 1. So this will be minus 1.5 volts. Correct? So now our equation now becomes V1 plus 1.5 by 3 plus V1 by 2 equals 1 ampere actually. 1 ampere is entering. Correct? So 5 V1 by 6 is minus 0.5. Getting the same answer.
Yeah.
Right? You're getting minus 3 by 5.
Correct.
Obviously, the voltage potential difference between A and B should not change, no? If the answer is consistent. Yeah. And now if it's minus 3 by 5, that is R Thevenin is plus 3 by 5. Correct, no? So 1 minus 0.5. So V1 is this correct?
Is it minus V1?
Let's see. Oh, it's plus plus 3 by 5.
Yeah.
Correct. It has to be.
Correct.
So because now the polarity of V1 will change, no? Because you've changed the direction of current.
Correct.
That is correct. So it will be plus 3 by 5 and R Thevenin will be 3 by 5.
Yeah. 3
Perfect.
by 5.6.
So that is V1. 0.6 ohms.
Oh, so this is nice way.
Yes. So correct. In fact, this was faster. Like 2 steps.
But in the previous case, you have put current in the other direction.
I put the current in the other direction.
Just to make the, because I1 was marked in that.
I1 was marked in that way. So I just did that to make it easier.
It doesn't matter if, as long as we.
You are consistent with the polarities.
Yes,
that is all.
Yes.
Correct.
Nice. What else we should do?
Maybe we'll choose one more problem. It may be a different type of source. I think we have seen this one was a current controlled voltage source.
Yeah.
And I think we did so current controlled voltage source also. Let's do something else, maybe a current source of some kind. Maybe a current controlled current source, if they have it, might be interesting.
Voltage control current.
That is good enough for us. We just wanted a current source, no?
Yeah.
Control current source. Let's do that.
Yeah. This is also easy to.
Okay.
Yeah. So we have 4 volt. DC,
DC, no?
Yeah.
1 minute, I'll change it to black.
Yeah.
Redraw it. There you go.
Then from the top 2 kilo ohm. From there downwards, current source is in the upward direction. Sorry, it's a dependent.
Oh, it's a dependent source. Yeah. Okay.
That's Vx by 4000.
Okay.
And then that on the top, a 3 kilo ohm resistor.
Oh, 3 kilo ohm resistor.
Going to A.
Okay.
Yeah. So yeah.
This is B.
Yes. Vx is actually Vth itself.
So here. Okay. Yeah. Oh, I see. Okay.
So we can maybe mark it as Vx.
We can mark it as Vx. Correct. Yeah. We should mark it as Vx.
Yeah.
Okay.
Or if you want to complicate a little bit more, we can put an additional 8 volt here.
Before A.
Yeah.
Okay.
If it's
why not? We'll do that.
Like
this. Oh, 1 minute.
Vx is retained there.
Vx is retained there.
Yeah.
But only A moves, no?
Correct.
Okay, we'll do that. That is easy. Okay.
Because it's the first question we are solving.
Yes, correct.
And Vth and Vx at same node, it's
correct, that's right. So this is okay?
Yeah.
And you wanted an 8 volt, huh?
8 volt.
Polarity, which way do you want to have?
Minus plus.
Minus plus.
Yeah.
Okay, very nice.
Yeah.
So we want the Thevenin equivalent across AB.
AB.
Both VTH and RTH is what we want, no?
Yes.
Okay. Okay, let's do it. So, okay. So, if we want VTH, what we said earlier was we would find the open circuit voltage.
Correct.
Correct? I think that should still be valid.
Yes.
If this is AB is open circuited, all the current will flow through this. Correct?
Yeah.
So, let's see. If that is open circuited, so I'll just mark this. So Vx by 4000 will flow like this.
Correct.
You can write the maybe the
So 4 volt.
so this will also be Vx actually,
Correct.
right?
Because there is no drop in.
There is no drop across 0.
Yeah.
This is 0 volts.
Yeah. So 4 volt minus 2k into this current
Correct.
is Vx.
Correct. So 4
4 minus
Vx by 2k is Vx by 4000,
Yeah.
right? By basically 4k, right? So 2 milliamperes is Vx by 2 plus Vx by 4, no? So just
is it plus or minus? 4 minus Vx. 4
this is Vx, no? So this is Vx.
Yeah.
So 4 minus Vx. Correct. It will be correct. You are right. It will be opposite because the current is flowing like this.
Yeah.
Correct. So it will be. We should do it like this. 4 minus Vx is the current flowing in the opposite direction. So this should be minus Vx. So then it will just be Vx by 4000. So it will be Vx by 2000 minus Vx by 4000. That will be Vx by 4000.
Yeah.
So Vx is 8 volts. Is that correct? Let us see. So this current then is 8 by 4 2 milliamperes. That's what we saw, right?
Yeah.
Correct. So Vx by 4000 is 2 milliamperes.
2 into 2.
Correct. 4 volts.
It's
So
coming
8
8
volts.
volt.
8 volts. Correct. So this current is Vx by 4000. So it is 2 milliamperes flowing this way.
Correct.
Correct? Very
It is
good.
correct.
So it is correct. Okay. So that is Vx.
Yeah.
We need to find out VAB.
Yeah.
This is 8 volts, no? So we need to add another 8 volts. In this case, because you gave the polarities like this, no?
Correct.
So it will be 16 volts.
Yeah.
So this is plus 8. You are going up in potential by another 8.
Yes.
I was worried that
It's opposite.
it is opposite. Then we'll get a VThevenin of 0.
So if it's opposite, then it will be 0.
It will be 0.
Yeah.
Correct. So right now, it will be 16 volts, no?
Yeah. Correct.
Okay. And now RThevenin we need to find.
Yeah.
So what we would do is we would short circuit the independent voltage sources. But now we still have this Vx. We need to apply a voltage and find out.
Yeah.
Okay. So let's do that. So like this. And 8 volts is short circuited.
Vx will still.
Vx will still mark.
Yeah.
So we'll just mark Vx here.
Yeah.
And now we can apply a voltage, no? Voltage source, no?
Yeah. 1 volt.
1 volt will apply. So apply 1 volt, Vx is 1 volt.
Correct.
So this will just be 1 by 4000.
Yeah.
So you'll have 3 kilo ohms here and 2 kilo ohms here.
Yes.
So
Here maybe we can do source transformation. No?
we can do source transformation now for these. So now this would just be current is flowing like this, no? So
Plus, minus.
the current through this is flowing like this, no? So it should be plus and minus, correct?
Correct.
Okay. Okay.
3K.
3K. 1 by 4. So this will be 2 kilo ohms and you have another 3 kilo ohms. And this would be 2K into 1 by 4000.
Yeah.
So 0.5 volts.
Yeah.
Okay. So now we also have 1 volt here.
Correct.
And we want to find out the current, no?
Current drawn from?
Current drawn. So this is some I.
Yes.
Right. So this is the I that we want to find. Yes. So that is easy. So it is just 1 minus 0.5. So 0.5
by 5.
By 5K. 5 kilo ohms. So that is 0.1 milliamperes. 0.1 milliamperes. Okay.
So the resistance is?
So the resistance is 1 by I. 1 volt by I. So this is 1 by 0.1, 10 kilo ohms. Okay. Good.
Nice.
Easy, relatively straightforward.
Yes.
Right? You just need to keep track of the polarity signs very carefully.
Oh, so we have done both. I mean, previous one we have applied current.
Correct.
And then found the RTH. Here you have applied 1 volt.
1 volt and found out the current and taken the inverse of that. So all of them, both of them will give the same answer.
Yes. Super. Should we just draw, just for the sake of completion, we'll draw the Thevenin.
Draw the Thevenin equivalent. Okay. So what I will do, I'll draw it here. So the Thevenin equivalent. So across A and B, no?
Yeah.
So we said R Thevenin is 10 kilo ohms and we open circuit was 16 volts. So this is your Thevenin equivalent.
So in the Thevenin equivalent, we don't see that.
You don't see that control source.
Yeah. Because we have already taken care of.
We have already taken care of everything. Correct.